All right, this is the beginning of chapter 6 on momentum. And in chapter 6, we're going to deal with basically three things. And that is, first, just defining what momentum is. So first, we'll just define momentum. Learn how to calculate the momentum of a particular object, mass and velocity. Second, we'll look at impulse. An impulse is just our change in momentum and how we can use that to determine the force. And actually, we'll learn that this is actually how Newton, Isaac Newton that is, how he came up with the Newton's second law and how he framed this whole idea of Newton's second law is in terms of the impulse. And then finally, we'll look at the conservation of momentum in collisions, in two different types of collisions, elastic and inelastic. So there aren't that many things involved in this, and most of the stuff is fairly straightforward. But as with any topic, it requires a lot of practice, and it's actually going to be building on a lot of what we've done already. So if you haven't been able to master that as of yet, then you'll have trouble moving on from here. So I encourage you to go back and to review that material. Now, linear momentum is just a measure of the object's mass and velocity. So it's the product of the mass and the velocity. It is a vector quantity, so we'll draw it with an arrow. It's equal to the mass, which of course is a scalar quantity, times the velocity. And again, the velocity is a vector quantity. So this product is a vector. We use a lowercase p to describe momentum, lowercase. The SI unit for momentum, no fancy units here. It's just going to be kilograms, meters per second. And as I said, momentum is a vector quantity. Here's a quick test, which you'll find on the quiz coming up. Don't forget that kinetic energy is a scalar quantity. It is not negative, it's only positive. And momentum is a vector quantity. Now, from Newton's second law, we can say that F equals ma. We know F equals m times a, the mass times the acceleration. And then we also know from our discussion on kinematics that the acceleration is equal to v over t, or change in velocity over our change in time. That is the very definition of acceleration, that it is some change in velocity in a given amount of time. And so I can rewrite this, and I can say that force is equal to mass times my change in velocity over my change in time. And then I can further recognize that since momentum equals m times delta v, then I can see that this force is equal to a change in momentum over a change in time. So this is Newton's second law, and actually this is the way that Newton wrote his second law in looking at the momentum. Now, this change in momentum, I think it's on the next page. This change in momentum is called the impulse. So the impulse, which we'll call I, is equal to our change in momentum. So anytime I don't know why they do this, like why you can't just say change in momentum, but impulse is the change in momentum, and that's sort of standard fare. It's defined as the change in momentum. So then, if we go back to what we had before, which was that F equals delta P over delta T, then if I is equal to our change in momentum, then our impulse, which is just our change in momentum, equals F times delta T. That means that if you have a change in momentum for an object in a given amount of time, then it's easy to find the force. And the change in momentum is fairly easy to find. Forces, by the way, are very difficult to measure, right? Especially in collisions. But changes in velocity, and hence changes in momentum, are very easy to find. So let's imagine this. I have a car that has a mass of 1,000 kilograms, and it collides into a wall. And it's initially traveling 10 meters per second to the left. I have here, so that's a negative 10 meters per second. It hits the wall and rebounds back at 2 meters per second to the right. Now, if the collision occurred in a tenth of a second, what force is imparted to the person in the car? Okay, well, I know that F is equal to I over delta T. That's my force is equal to my change in momentum over delta T. And actually, I'm going to be writing this just as delta P over delta T. And you can do what you like. I find this a little easier. Just instead of referring to it as impulse, I'll just refer to it as change in momentum. However, you do need to know that this impulse and change in momentum, that those are the same things. Not necessarily, not for this class necessarily, but for the wide world. All right, so my force is equal to my change in momentum over my change in time. And my change in momentum is just going to be my final momentum minus my initial momentum over my change in time. My final momentum is my mass times my final velocity minus my initial momentum, which is my mass times my initial velocity, over my change in time. Okay, so I have all these values, so it's fairly easy for me to calculate the force, even though it's very difficult to measure that force. So I have 1,000 kilograms. My final velocity is 2 meters per second to the right, so that's positive 2 meters per second, minus 1,000 times negative 10 meters per second. Because my initial velocity was 10 meters per second to the left. And I'm told that all this happens in a very small amount of time, about a tenth of a second. If I solve that, I get that in the numerator, I get 12,000 is my change in momentum, and that's going to be in kilogram meters per second over 0.1, which gives us a force of 120,000 newtons. So that is the force imparted onto the car, causing it to come to rest, actually to bounce off this wall somewhat, and a fairly, I wouldn't say a minor collision, but at about 20 miles an hour or so, hitting this wall at about 20 miles an hour in about a tenth of a second, and then rebounding requires a force of about 120,000 newtons. Now, obviously, if you're a person inside the car, you're not going to feel that whole force, but you will feel a good portion of it.